Iodine, ma'am. Iodine violet.
So your solution will develop violet or blue color initially, and then when you will start titrating it with standard thiosulfate solution, it should get clear. Okay, so this will be the color change. So while performing this, we will be determining the amount of oxygen by the titer, and how we will correlate it with. So I will show you that 1 mole of your oxygen, it will react with 4 moles of thiosulfate. Okay, so we will see it in this next slide. Just a minute. Okay, so in the first step, before we will perform, we will take our sample solution, and that sample solution will be taken up in a reagent bottle, and then we will add manganese sulfate or manganese sulfate, and then we will add alkaline potassium iodide. So it will be alkaline by using sodium hydroxide. Now in this alkaline solution, your dissolved oxygen, it will oxidize, it will oxidize manganese plus 2 ions to give you manganese 4. So this is not a single step. There are many steps to this reaction. If no oxygen is present, so this Mn will directly react with the hydrogen ions present in the water. But if oxygen is present in the water, it will some of this manganese too, it will react with your oxygen to give you manganese oxide, that is Mn plus 4. Further oxidation is taking place. So how you will evidence it? By observing brown precipitate. Then here they are adding acidified potassium iodide, but we can add it with the alkaline solution. Then you will get brown precipitate for some time. You will allow it to settle down. This brown precipitate will settle down. If there is no oxygen, you will get this manganese hydroxide. Okay, so this is white in color. The PPTs are white in color, but some of the manganese will react with the present oxygen. Then eventually you will get brown precipitate. You will allow it to settle down, and then later on we will add some acid here, sulfuric acid, so the precipitate is again dissolved back into the solution, and by this we are we are limiting the present oxygen of the system, so that now we can keep this for longer period also. There will not be any chemical change. Otherwise, if your bottle is kept open and we have not dissolved that PPT, then there may be any change. So now later on what we will do, we will take up this solution. This solution will be titrated with sodium thiosulfate. So what is going to happen? Your Mn plus 42 will be reduced to Mn plus 2, and you can see in this step iodine is liberated, but when this liberated iodine will be titrated up with this sodium thiosulfate, we'll be using it, and we will you will add some amount of this sodium thiosulfate so that you will get pale yellow color, and then afterward you will add uh, 2 to 3 drops of your starch indicator, so you will get dark blue color because your iodine is liberated. Now your this liberated iodine will be titrated up with the sodium thiosulfate. Okay, so in this you can see that 1 mole of O2 is here, it is reacting up with 2 moles of to give you 2 moles of MnO2, and this 2 moles of MnO2 will give you 2 moles of iodine. This 2 moles of iodine will give you 4 mole, it will reacting up with the 4 moles of sodium thiosulfate. So ultimately what we can correlate, that 1 mole of O2 for 4 moles of sodium thiosulfate. So you can thereafter, determining the number of moles of iodine produced, we can work out the number of moles of oxygen molecule present in the system, because they are related to each other with this titer. And here we will report the oxygen content by milligrams per decimeter cube, or in simple terms by parts per million. So your oxygen is fixed when your MnO2 is precipitated. Then you are fixing it up by acidifying the solution to the pH between 2.5 to 1 by adding acid. Then your PPT is dissolved, and your liberated Mn plus 4 or Mn plus 3 ion here, it will oxidize your previously added iodide ions to iodine. So the Ki which has been added previously, it will be oxidized to give you iodine. Okay, then this iodine, it will form complex with the surplus iodide ion which is present to give you triiodide complex. This will further be titrated with thiosulfate. Okay, so what thiosulfate, your iodine will again be reduced to iodide, so you will get a colorless change from blue to colorless, and thiosulfate will be oxidized to give you tetrathionate here, this last step. Okay, so Mn plus 2 with hydroxide with water, manganese hydroxide. This manganese hydroxide will again react with the present oxygen and water to give you this state. And this, or you can say manganese oxide, will react with the present iodide to give you to liberate the iodine. This liberated iodine again will it will combine with the surplus iodide ion to give you triiodide complex, which will be titrated up with sodium thiosulfate. Now here we should use standardized thiosulfate, and it is standardized by using potassium iodate. These are the steps. This is our reagent bottle for the determination of DO value. Then sample is taken up, then manganese sulfate is added here. Then we will shake this bottle, and we will then keep it up for some time. Then we will add alkaline solution of potassium iodide in the same bottle. We will shake it up. After getting after this, we will get brown color PPTs. If we are getting some bubbles, then we should discard that sample. Otherwise, we will proceed further. We will keep it up for some time. Then we will add sulfuric acid to dissolve the reddish brown precipitates. And then after some time, we will titrate it up, it with up sodium thiosulfate. Okay, and we will use starch as the indicator. So as you will add starch, then at the initial stage of the titration, you will get dark blue color because iodine is present. And then as you will gradually add sodium thiosulfate, then that complex will be broken up, and you will get a clear solution because now your iodine is converted to iodide. So color of the solution will change to colorless. Okay, so just a minute. I hope it is clear to everyone till here. Students, am I audible to everyone?
Yes, ma'am.
Okay, so this portion is clear, right? And the steps are clear. Okay, now I'm going towards the calculation part. See, 1 mole of oxygen is required for is reacting with 4 moles of sodium thiosulfate, right? So 1000 ml of 1 normal sodium thiosulfate requires 8 grams of oxygen. 4 moles requires 32 grams. Okay, so what about 1? So for 1 it will be 8 grams, right? So this is for 1000 ml, 1 normal. Now we have used this much, this reading. Okay, this is reading which we have got after titration. Suppose it is xml. Okay, so what will be for this, how much oxygen will be reacting with this xml? So for this xml it will be x multiplied by whatever normal or molar solution of sodium thiosulfate we have taken. So here, since we have taken 0.001, so that multiplied by 8 grams. So you can see it is 1.456 milligrams, right? Now we will convert this to ppm. So the total capacity of our reagent bottle is 300 ml. We have taken the sample here 200 ml. So in 200 ml we are getting 1.456 of milligrams. So what will be for 1000, because we want to convert it to parts per million, 1 liter. So we will calculate it for 1000 ml. So this has been converted to now parts per million. You can see it is somewhere around 7.28 parts per million. So dissolved oxygen in the given water sample is found to be 7.28 ppm. You will find out the basic details like we have taken here 14 grams of manganese sulfate into 50 ml water. We have prepared basic iodide solution by dissolving 12.5 grams of Ki and 6 grams of NaOH into 50 ml. We are preparing 250 ml. Okay. Then we have taken up here 0.01 normal sodium thiosulfate, concentrated H2SO4 and starch indicator. So first of all, we will take one stoppered flask. We will add 200 ml sample water. We will add 1 ml of manganese sulfate solution, and then we will add 1 ml alkaline iodide solution. Then what we will do? We will fix the oxygen. How? We will immediately stopper the bottle. Then we will shake it up for 10 minutes. Then if what will happen? First of all, your this manganese sulfate, it will react with the water hydroxide ions. So you will get white ppts to give you manganese hydroxide. Okay, then if some of the manganese sulfate is left, then it will react with the further oxygen which is present in the solution, and you will get manganese oxide. Okay, and you will observe brown colored precipitates. So your Mn plus 2 will change to plus 4 and you will evidence it by the formation of reddish brown precipitates. Then we will allow it to settle down for 10 minutes. Then after 10 minutes, you will see clear liquid is in the upper portion. And then after 5 minutes, we will add 1 ml concentrated H2SO4 solution so that it is dissolved. Why? Because it is directly indicates the presence of oxygen in the solution, those reddish brown precipitates. Okay, so we will fix it up by adding the acid, and then we will again we will open it for adding. Then after addition, we will again stopper the flask. We will mix the content in the flask, and then precipitates will be dissolved. You will get a clear yellow solution. Why you will get clear yellow solution? Because iodine is liberated, and that iodine will combine with surplus iodide to give you triiodide complex, and its color is yellow. So you will observe yellow solution. Now this quantity of the liberated iodine, it is equivalent to dissolved oxygen of the original sample which we have taken up here. So then we will take up this solution to for titration with 0.01 normal sodium thiosulfate. Okay, so this is all about the procedure. And just a minute.
So today we'll be determining for dissolved oxygen, that is DO. So as you can see here, we have prepared the reagents before as per the procedure given in the manual. The reagents are manganese sulfate, alkali iodide azide, and then starch indicator, and we'll be taking standard sodium thiosulfate in the burette, and we have taken concentrated sulfuric acid. So all the reagents are prepared using the procedure given in the lab manual. So as a sample, we'll be taking STP water, that is sewage treatment plant water. So this is a BOD bottle of 300 ml capacity. So the sample is being filled in the BOD bottle. It is filled completely. Now the reagents, that is manganese sulfate and alkali azide of 2 ml will be added. 2 ml of manganese sulfate is measured. And is added to the sewage sample. This is alkali iodide azide. 2 ml of alkali iodide azide is measured. This is added to the sample. As you can see, there is air bubbles in that. A tiny air bubbles are created. So before titrating it, mix it well until the air bubbles are vanished, and then allow it to precipitate. It is being mixed well in order to eliminate the air bubbles which are trapped inside. Once all the air bubbles are eliminated, allow it to precipitate before the titration. After a while, you can see that it has precipitated completely. Now we'll add concentrated sulfuric acid. So 2 ml of concentrated sulfuric acid is added to the sample after the precipitation. So you can clearly see that it is turned into dark straw color. Now exactly measure 203 ml of sample from the VOD bottle and take it to the conical flask. So exactly 203 ml of sample is taken from the VOD bottle, the conical flask, to titrate it against sodium thiosulfate solution. So now the solution will be titrated against standard sodium thiosulfate solution until it turns to pale straw color. So as you can see, from the dark straw color, it has turned to pale straw color.
This is your pale yellow color solution.
Few drops of starch is added to the titrated solution now. After the addition of starch, it has turned to dark blue color. Now titrate it until it appears to be colorless. So you can observe that from dark blue color, it has completely appeared to be colorless. Note down the
Then we will note down the reading and then we will perform the calculation. So this Winkler method is clear to everyone. I will also share the link. Okay. Now we will see the second point, that is chemical oxygen demand. Okay. So this is also shortly known as COD, and in that sample to get decomposed. If there is any biological, then we will say that it is BOD value for organic, and if it is for chemical, we say it is an COD value. Okay, so it is nothing but it is the amount of the specified oxidant, that is oxygen, which will react with your sample under the control condition. Okay, and again here the consumed oxidant which we will be using here, we will express it in terms of oxygen equivalence. Okay, so COD is used to measure the pollution level of the sewage system or wastewater, okay, or natural water system. Similarly, there are few others value also, like total organic carbon TOC, total oxygen demand, that is TOD. So this TOD is BOD, COD together is total oxygen demand by biological or chemical matter present in that sample. Now as an oxidant, we can use n number of oxidant. There are various numbers of method, okay, but in this method specifically, we will use an oxidant, that is potassium dichromate. We may also use potassium permanganate, okay, but we are using potassium dichromate here because it is a very good oxidant. It has unique chemical property, and in this method your chromic ion will be generated. Okay, so dichromate will be reduced to give you chromic ion. Now your sample contains both organic and inorganic matter or component. Okay, so what we will do, basically organic component, it predominates, and we calculate organic matter because it is of greater interest to us. So here we will use this oxidant to decompose or oxidize uh, this organic matter. Okay, so we will call it as a COD defined test. So the extent of sample oxidation, it can be affected by digestion time. What is the time, what is the strength of the reagent which we are using, okay, and what is the sample COD concentration. It means if there are other components too, inorganic components, like sometimes presence of the halides, it also interferes, and so we get error in the measurement of COD value. Okay, now, if hazardous wastes of mercury will be okay in this COD analysis, hazardous waste of mercury and hexavalent chromium ion, sulfuric acid, silver, and other acids will be generated. So before we perform, we should know what will be the generation after the procedure. Okay, so that we can manage it. So you may say that this may be the disadvantage also of this procedure. Now here we will be using this indicator. Okay, this is nothing but 110 phenanthroline, and this is your ferroin indicator. We will be using ferroin indicator for this process. So first of all, our sample, it will be reacted up with uh, potassium dichromate and acid. So collectively they will give chromic acid. This chromic acid is very strong oxidizing agent. It will oxidize all the organic matter which is present in the sample. Then initially when we will add, your color will be orange red. Then we will allow it to reflux for 30 minutes. Okay, so after 30 minutes, after the decomposition, okay, the waste, it will react with this potassium dichromate. Okay, and it will be chemically oxidized. So the color will be orange red. Okay, then after this, it will be allowed to cool. During this color is during reflux, then when it is allowed to cool, this will be the original color, green. So when we will start titrating it with up ferrous ammonium sulfate by using ferroin as an indicator, so what will happen here, when the endpoint will be over, this reddish brown color will appear. So this will release Cr plus 3 ions after the completion. Okay, so in this what we are doing, we are taking sewage water, then we will add our potassium dichromate, we will add acid, strong acid, we will add silver sulfate, we will add mercurous sulfate, and then we will reflux it, we will allow to cool, then we will add 3-4 drops of ferroin indicator. Now going back to the journal, you will find the principle that this COD determination is based on chemical oxidation. We are chemically oxidizing the organic matter which is present in our sewage sample by using potassium dichromate, and this COD value is a characteristic value to determine the organic strength which is present in that water sample. It also denotes about the pollution of that water system. So in this standard procedure, we will know, we will take up a known quantity of a standard reagent, that is potassium dichromate, which is performed by the acidic solution of concentrated sulfuric acid. We will be add silver sulfate. This silver sulfate is added as a catalyst. Why? Because sometimes some aromatic moieties which are present in the system, they resist this oxidation. Okay, then we may have a straight chain aliphatic moieties, but when we will add this silver sulfate, it will fast up the reaction of the oxidation of this aliphatic chain moieties. So this will act as an catalyst. Okay, so after this whole thing, it will, this whole mixture, it will be allowed to reflux for 2 hours. We will reflux it for 2 hours. Why? Because we want to ensure complete chemical oxidation. Okay, now most of the organic matter which is present here, it will be destroyed in the boiling mixture of the chromic acid. Then we will allow it to cool. We will also add mercurous sulfate here. this mercurous sulfate is added so that if there is any halide present in the system like chloride, bromide, iodide, so they may interfere with silver sulfate. They may interfere with this silver to give you a precipitate of silver chloride. So your catalyst will not work. It will be trapped. So to remove that interference, we can use mercurous sulfate. Then afterwards, we will titrate this whole mixture after cooling with standard ferrous ammonium sulfate, and while that time we will use ferroin as an indicator. So here we have prepared 0.2 normal of potassium dichromate by 8 molar H2SO4 solution. So for that, we need to weigh this much gram of potassium dichromate. Then we will carefully dissolve this into 8 molar H2SO4 solution. Then we will slowly make it up to 1000 ml or 1 liter. Then separately we will take we will take solid silver sulfate. Then we need to prepare ferroin indicator. This will be, its strength will be 1%. It will be prepared up in water. Then you can see that since we are taking 0.2 normal potassium dichromate, so in the same side we will take 0.2 normal FAS for the titration. Okay, so this is the weight which is given here for preparing 0.2 normal ferrous ammonium sulfate solution of 1 liter. Now we will take 50 ml of the sewage sample. We will add 20 ml. 20 ml is now known to us, okay, of the oxidant, chemical oxidant, potassium dichromate. Then we are adding 0.1 gram of the silver sulfate. We will reflux it for 2 hours. We will cool it. Then we can add mercurous sulfate, and then we can titrate it against ferrous ammonium sulfate. Okay, so we will note that reading as V1 ml. Now similarly again we will perform one more titration, but here now we will not use the sample. We will take each and every reagent, but in place of sample we will be taking double distilled or deionized water. Okay, so that will be taken as in blank. We will note down the reading as V2 ml. Okay, so why we are doing? Because we want to know about the we want to eliminate the interference, okay, of the reagents. Now for 1000 ml 1 normal FAS, we need 8 milligram. So for 1000 it will become 8000. So your V2 is the blank and V1 is your sample. So for V2, this will be around 16.6 ml of the sodium thiosulfate, because there the potassium dichromate, it will not be utilized up here because there is no chemical substance which is present for oxidation. But in case of our samples, our sample contains the organic moiety, organic content as in pollutant, so it will utilize some of the chemical oxidant. So some will be taken up and some will be left, which will further react with this ferrous ammonium sulfate. So by calculating the difference between the two, you can see what we are doing. We are subtracting V2 minus V1. V2 is for blank, V1 is for sample, right? So how much oxygen will be present for this much for the sample? So this difference will be multiplied with the milligrams of oxygen here, multiplied by the normality of the ferrous ammonium sulfate, and it will be divided up by 1000, okay, for liter. So it is coming up around 11.36 of milligrams here. Now this much is present into 50 ml because we have taken 50 ml sample. Okay, so what will about how much will be present in 1 liter? So now we are turning it up into ppm. So this is somewhere around 227.2 ppm. So you will report it as the chemical oxygen demand of given sample is found to be around this much ppm. Is it clear to everyone? Now we will see this video, how we will perform the determination of COD of the wastewater.
Myself, Kiran Kumar P, Assistant Professor, Department of Chemistry, ATME College of Engineering, Mysore. COD is a chemical oxygen demand. It is the amount of oxygen required to chemically oxidize all organic impurities present in wastewater sample. It is expressed in terms of milligrams of oxygen per liter. Let us move on to experimental part. The chemicals required are, we need a water sample, K2Cr2O7. We need 1:1 H2SO4, which contains silver sulfate. We need an indicator. Indicator is indicator. Now prepare a standard solution of salt. Pipette out 25 cm cube of water sample, 25 cm cube of K2Cr2O7 into a conical flask. Add 20 cm cube of 1:1 H2SO4, which contains silver sulfate, which acts as a catalyst. Now add about 2 to 3 drops of ferrion indicator. Titrate the solution with standard FAS filled in a burette. Till the color changes from bluish green to reddish brown. You can see the color is about bluish green.
Please observe how the color is changing from bluish green to reddish brown.
Now you can see the color is changing. Titrate the solution carefully. Now you can see reddish brown color occurs. Note down the final reading. Let us move on to calculation part, where in the calculation part A is the preparation of standard FAS solution. With the help of given weight of FAS, calculate the normality of
So with this, we have completed here the determination of DO value and COD value for a given ETF water sample or sewage sample. Now we will see the third practical. Here we will determine the content of iron present in the iron tablet. So let's have a look towards the aim. Determination of iron in iron tablets. The determination here, it is based upon simple, you can say, EDTA titration. And here we will not, we will use salicylic acid as an indicator. This is the electronic configuration for the iron. I hope all of you can see this. Okay. Now let's have a basic look towards the use of iron, where it used and its properties. It it is a metal, it is a silvery white magnetic metal, reacts with moist air, and it is readily dissolved in acids. Then we use the cast iron. We use iron for making steel alloys, and steel alloy basically contains carbon, chromium, tungsten, nickel, and iron. Carbon steels like mild steel, there we have 0.1% to 4% of carbon. Then in stainless steel, we add chromium to get an alloy, to get good anti-corrosive property. Then for surgical instrument and for cutlery, we also add nickel. Okay, so when we use this combination, that is iron plus carbon plus tungsten, we get very tough. But when we add iron, carbon, and manganese, we get hard wearing material for cutting tools. Then iron is also used in steels for making electromagnets. Then iron sulfate, that is Fe plus 2, FeSO4. Okay, it is used for medicinal purpose. It is used in vitamin tablets as a source of iron. Then iron plus 3, that is ferric. Uh, it is used for other purposes, and its color is yellow. And iron plus 2, when it is in plus 2, it is light green color. Then what is the biological role of iron? So it is an essential part of our diet. We need it because to produce hemoglobin, it is an essential part in the hemoglobin. Then in the hemoglobin, this iron atom, it helps to coordinate oxygen molecule for the transportation of oxygen in our cells. The deficiency of this iron can cause anemia, and this iron in plants is replaced by magnesium to give you chlorophyll. Now you know that it is a member of 3D block. Okay, but is it truly a member of first transition metal series? So if you look at the configuration of this Fe plus 2 and Fe plus 3, so what you will find that they both have an electron configuration where they have partially filled 3D subshell. Okay, so This is the most important criteria for considering any element to be as a member of this 3D block transition metal. So for Fe plus 2, you can see this is 3D6. For Fe plus 3, it is 3D5. For both ions, for Fe plus 3 and Fe plus 3 and plus 2. Okay, so what is happening? At least one electron, it can be promoted to higher level when the 3D subshell is splitting, and when it will split, when your central metal ion, which is Fe, it will interact and it will form bonds with the ligands. Now this is your salicylic acid, very common. Now going through this practical, first of all we need to prepare our sample. So for that we will crush 2 iron tablets in a mortar and using pestle. Then after crushing, we will triturate it up with 10 ml of concentrated nitric acid. We will boil this solution for 30 minutes and then we will dilute it with 200 ml of water. And if it is clear, then we need not to filter, but if it is not clear, then we need to filter this solution. Then further, this filtered solution, it is diluted up to 500 ml using a volumetric flask. And for this, we will use distilled water. Now, FeSO4, okay. So in ferrous sulfate, it is used for medicinal purpose and as a source of iron in vitamin tablets. This Fe plus 2 is further oxidized to Fe plus 3. Okay, how? By refluxing it with, by boiling it with nitric acid. So the concentration of Fe plus 3 in the sample solution, it will be determined after cooling this solution. So we will cool up the solution where Fe plus 2 is converted to Fe plus 3. We will titrate it up with EDTA. Now how the complexation is taking place? So it is taking place by 1:1. So it means each mole of EDTA complex, it will form complex with 1 mole of Fe plus 3 to give a mole of FeEDTA complex. Okay, and this reaction is carried out by titration. Here we will very slowly and gradually add EDTA from the burette until we reach up to the end point. After reaching towards the end point, we will note down the amount of EDTA. We will take this as a signal and then we will calculate the moles of Fe plus 3 which is present in the solution. In this experiment, salicylic acid is used here as an indicator which will form intensely violet colored complex with Fe plus 3 in acidic pH. Initially, when we are starting up the titration, we are taken the boiled solution and it is boiled up with the acid. Okay, so in that case you will get intentionally violet colored complex, and this complex is formed with salicylic acid and Fe plus 3. Now later, when slowly and gradually we will proceed with the addition of EDTA from the burette, what will happen? This Fe and Fe plus 3 and salicylic acid will break. Why? Because the formation constant for this complex FeEDTA is on the higher side. So what will happen? Slowly there will be color change from intentionally violet towards light yellow, and then at the end point it will go to colorless. So actual reaction will look like this. This is your salicylic acid plus Fe plus 3, and this is the Fe and salicylic acid complex. This is of intense violet color. Then we will, after the addition of this indicator, we will start up adding EDTA. Okay, so this is your EDTA. Now the color will change to light yellow, towards light yellow. So here the formation of EDTA with iron, this complex is favored over the complex of salicylate complex, because the former, that is your EDTA complex, it has greater formation constant, उसकी बनने की शक्यता ज़्यादा है. Okay, so original solution will be of dark violet because of the presence of Fe salicylate complex, and when we will proceed towards the titration, the solution will retain reddish color until we have added enough EDTA. Okay, but when enough EDTA is added, it will react with all the original iron salicylate complex, and at that point the final traces of red color will be disappeared, and we will see only pale yellow color of iron EDTA complex. So we are moving towards the known concentration of EDTA. वो हमको ब्यूरेट में से मिल जाएगा कि कितना वॉल्यूम हमने EDTA का यूज किया, कितना ऐड किया, और उसके ऊपर से we will calculate the concentration of iron in the sample solution. So the calculation, it will look like this. So for 1000 ml 1 molar EDTA, we will need 1 mole of iron. It means 1 mole of iron means 55.85 grams of weight. Okay, तो जो भी हमारा वॉल्यूम आया है ब्यूरेट से, उसके लिए कितना चाहिए? So suppose it is X or V1 ml. So for that V1 multiplied by आपने कितना नॉर्मल या मोलर EDTA बनाया? So that is, यहाँ इस केस में हमने 0.01 मोलर बनाया है. So we will multiply it with 0.01 molar multiplied with the molecular weight. So again, this is present in 10 ml solution. 10 ml solution में इतना है, बराबर? तो हमने कितना solution बनाया था टोटल? 500. तो 500 में कितना होगा? So here, after calculation, 173 milligrams is present in 500 ml solution, and we will write it, we will report it like amount of iron in iron tablet in 500 ml solution. वो 500 solution हमने कितने tablet से बनाया? तो containing 2 tablets is so and so milligrams. This is how you will report. Now let me show you the video.
This practical is the determination of the amount of iron in some iron tablets, and the iron tablets I'm using are Ferrograd tablets. The glassware apparatus required for this practical are a volumetric flask, 250 ml, 100 ml graduated cylinder, some 250 ml beakers, a setup for a burette and clamp, retort stand, and a pipette for measuring out our iron solution, and a white tile for determining the colour. We also need a pestle and mortar for grinding up the iron tablets, and a balance for weighing out the iron tablets before the start of the practical. The two chemicals required for this practical are a potassium permanganate solution, which I've already prepared, a 0.015 molar solution, and a sulfuric acid solution, and I'll be using a 1 molar sulfuric acid solution. With this practical, we need 5 iron tablets. So we're going to weigh the 5 iron tablets, put my clock glass onto the balance, hit the tare button to bring it to 0, and then pop out my 5 tablets. And weigh my tablets. So I have my 5 tablets weighed out, and now I want to dissolve up those 5 tablets in sulfuric acid water solution. But in order to do that, I need to grind down, using the pestle mortar, I need to grind the iron tablets. So into the clean mortar, I'm going to now start to grind the tablets. So in the iron tablet, the iron is in the +2 state. Iron will naturally oxidize from +2 to +3. And in order to stop that oxidation happening, once I've got my tablets finally ground down into a powder, I add in my 100 mils of sulfuric acid.
Now sulfuric acid is being added.
Grind that down a little bit more. And this should help dissolve the iron tablet, but also stop the iron from going from +2 to +3. Now the sulfuric acid is added, we can now transfer this washings into the volumetric flask. I'm going to transfer this iron solution into a clean, dry 250 ml volumetric flask. But as you can see, there's a lot of remaining compound in the pestle mortar, so I'm going to rinse that out with the remainder of the sulfuric acid. To ensure that all the washings are in the volumetric flask. Next, using the ionized water, I'll now fill the volumetric flask until the bottom of the meniscus is in line with the graduation mark on the neck of the volumetric flask. Add the deionized water until the bottom meniscus is in line with the graduation mark at eye level. Stop at that and invert it approximately 20 times to ensure I've got a homogeneous solution of the iron tablet dissolved in.
Your solution should be homogeneous.
With sulfuric acid added in order to stop the iron from going +2 to +3. Next, I want to take a sample of 25 mils of the iron solution. So transfer
So the
volumetric flask.
The titration, the volume will be for 25 ml. Okay, and so we will perform the calculation for 250 because we have prepared 250 ml solution.
And I'm using a 25 ml pipette. Put the tip of the pipette into the bulb so it's held firmly. Then press the button mark A to expel the air out. Then I'm going to draw water into the pipette to clean it. And then I'm going to press the button marked E, expel that liquid out. And now I have a clean pipette. There's a little drop remaining at the bottom, so I'm going to press the button marked S and squeeze out the last remaining amount of water. And now I'm going to rinse with the solution it's going to contain to ensure I don't dilute the solution. So again, draw the liquid up into the pipette. Now my pipette has been rinsed out. And now I can measure my 25 mils of the iron solution. So don't put the tip of the pipette right to the bottom of the solution because there are some precipitate particles at the bottom of the beaker. I'm going to draw the liquid now up into the pipette. This is a 25 ml pipette. So draw the liquid up until the bottom of the meniscus of the iron solution is in line with the graduation mark here at eye level. If you go too far, which I'll do on purpose, you can press the button marked E, and then the liquid level goes down until the bottom meniscus is in line with the graduation mark at eye level. Now I'm going to transfer this 25 milliliters of the iron solution into a 100 ml conical flask. This is a clean, dry conical flask. Put the tip of the pipette over the conical, press the button marked E and let the liquid run down into the conical flask. And then you will notice at the tip of the pipette there is a tiny drop remaining. Touch the pipette off the side of the conical flask, and we've now ensured that 25 millilitres of the iron solution has been transferred into the conical flask. Next, I need to fill the burette. So, fill the burette. First of all, ensure the tap is closed, so it's in the horizontal position.
The
And then
titration
I have
here,
my
it is
potassium
performed
permanganate
with different
solution,
reagent.
my 0.015 potassium permanganate solution,
Just a minute.
and fill the burette
Okay. So I have shared all the links for all the 3 practicals. In the third practical, the determination of iron, uh, I haven't found any video where we are using the salicylic acid, but it was developed uh, by us here, and it works very similar to the self indicator, which is potassium permanganate. So in this video you will find potassium permanganate, but in place of potassium permanganate we have used EDTA. Okay, so this can also be used, EDTA complex method, and we can also use self indicator potassium permanganate method. Both the methods can be used. Now if you have any doubt you can ask me.
हेलो मैडम, प्रैक्टिकल का जो मटेरियल है वो ग्रुप में भेज देना आप।
क्या मटेरियल है? कौन सा मटेरियल होता है प्रैक्टिकल का?
मैडम जो प्रोसेस है ना वो प्रोसेस।
अच्छा, वो आपको मिल जाएगा। आपको लिंक मैंने शेयर कर दिया है। और कुछ भेजना है? Okay, so with this now we have completed 3 practicals. One, the determination of dissolved oxygen. Second, determination of chemical oxygen demand for a given sewage water sample solution. And third, determination of iron in iron tablet. Okay, तो अभी आप ये 3 जो है मैंने लिंक शेयर किए वो आप देख लेना। आज बहुत सारे वीडियोस अवेलेबल है, आप वो भी देख सकते हो जो भी आपको अच्छा लगे या समझ में आए। लेकिन आज आप इसको समझने की कोशिश करना, और इसके जो क्वेश्चंस होंगे वो एमसीक्यू फॉर्म में ही रहेंगे। तो एमसीक्यू में जैसे हम कौन सा रिएजेंट यूज करते हैं, इस मेथड का प्रिंसिपल क्या है, कैलकुलेशन में हम पर्टिकुलर ये नंबर क्यों यूज कर रहे हैं, ठीक है, इस तरीके के हो सकते हैं। या यहाँ पर इंडिकेटर क्या है, ये इंडिकेटर कौन से पीएच पे वर्क करता है, ये सारी चीज, इस टाइप के क्वेश्चंस आपको मिल सकते हैं। तो आप इसके रिगार्डिंग भी प्रिपेयर कर लीजिएगा, ठीक है। सो नाउ हियर वी विल स्टॉप, एंड if you have any doubt you can ask me, or we can stop this meeting, so you can leave this meeting.